All right, this is 11.2, special cases in relative motion. For this video, we're just going to be focusing on the special cases part. In the next video, we'll do relative motion. So let's say you are in an apartment building, 10 meters up, and you see your friend walking below. And you, being the great friend you are, decide to chuck a water balloon down at them at 5 meters per second. Okay, and you want to figure out how long before the water balloon hits your friend. Okay, so after this video, we are going to have derived some equations that will allow you to figure this out. So what special case are we working with? Well, the case where acceleration A is constant. Right? Now, what is the acceleration on Earth? Well, it's the acceleration due to gravity, aka 9.81 meters per second squared in the downward direction. Okay, and that is true for, a range of altitudes, right? So as the water balloon goes down to your friend, the acceleration is roughly constant. Yeah, sure, up here gravity is a little bit weaker, so it's a little bit different, but it's negligible for this problem. Okay, so we're going to be working with the case where A is constant, and we're going to derive some equations based on that assumption that acceleration is constant. Now, what is the definition of acceleration? Well, it's the derivative of velocity with respect to time. Okay, I can rearrange this and get dv is equal to acceleration times dt. And so now I have my variable velocity v on this side and my variable t on the other side of the equation. So I separated the variables. So I can now integrate both sides. Okay, and I'm integrating time here from time 0 all the way to some arbitrary time t. Okay, now what is my velocity at time 0? Well, I'm going to call that v naught. So v naught is my velocity at time 0. Okay, now what is my velocity at time t, where t is just any number? Well, it's just some velocity v, okay? It could be anything. Okay, so at time 0, my velocity is v naught. At time t, my velocity is v. Okay, this integral right there is just v minus v naught. This integral right there, if you do the math, it's just a times t. Now, something important to note with this integral over here is you can pull out a. Here, I'll rewrite it. That is really just equal to integral from 0 to t. A is on the outside, dt. Okay, so we're able to pull a out because a is constant, remember. We're working under the assumption that a is constant. And that actually allows us to compute the integral as a times t. Okay, and then we can rearrange that and we get velocity is equal to acceleration times time plus v naught, and that is our first important equation. So if we have v naught, aka the velocity at time 0, and we know acceleration, we can find velocity at some arbitrary time. Okay, and that equation is only true again if acceleration is constant. Now, what is the definition of v, velocity? Well, it's v is equal to dx dt, and we just found v. What is v? Well, it's acceleration times time plus v naught, again if acceleration is constant. So you can rearrange this part and you get dx is equal to at plus v naught all times dt. Okay, so now I have my position x on one side of the equation and my variables time on the other side of the equation. So I've separated the variables, so now I can integrate both sides. Okay, let's bring this over here. Sorry, what is this integral? So what are our bounds of integration? Well, I'm integrating from 0 to some arbitrary time t. What is my position x at time 0? Well, I'm just going to call it x naught. So x naught is my position at time is equal to 0. And then what is my position at time t? Well, it's just some arbitrary position x. Okay. Now what is this left side equal to? That whole integral? Well, it's x minus x naught. And then a little bit more tricky. How about that integral? Well, it's a times t squared over 2 plus v naught times t, evaluated from 0 to t. And then we get x minus x naught is equal to a t squared over 2 plus v naught times t. Okay, and then I can arrange that for x, and I get x is equal to a t squared over 2 plus v naught t plus x naught. And that is our second important equation, again, if acceleration is constant. Okay, I guarantee you have seen these equations before in Physics 1. And so with this lower equation here, if I know acceleration, I know my initial velocity and my initial position, then I can find position at any time t. So going back to our problem up here with throwing a water balloon off a apartment building or tower, what is my initial velocity at time is equal to 0? Well, it's -5. It's negative because I define positive x as upwards and I'm throwing it downwards, so my initial velocity is -5 meters per second. What is my initial position? Well, it's +10. Okay, and then what is my acceleration? Well, the acceleration due to gravity kind of at sea level on Earth is 9.81 meters per second squared, and that acceleration is downwards towards the center of the Earth, and because downwards is -x, my acceleration a is -9.81 meters per second squared. Okay, and I want to find when the time when the water balloon hits the ground. So the time when the water balloon is at x is equal to 0. So x is equal to 0, and then I can plug everything in. I get 0 is equal to -9.81 t squared over 2 minus 5t plus 10. And then I can use the quadratic formula or any of your favorite methods and solve for t. And that'll give you the time it takes for the water balloon to get to x is equal to 0, aka the ground, aka your friend. All right.